Hey everyone, how's it going? This is Siri and I'm back once again with another PyTorch video. So we've moved on from tabular data, we've moved on from time series, right? And which was just another form of tabular data. And now we're going to be working with text data, which is not in a data table like it was in our past few videos. So we're actually going to be dealing with text, like paragraphs and things like that. And this sort of falls under the subset of natural language processing, right? So we have some natural language processing, and it's just what you think it is, right? We process and really try to understand and make predictions and analyze English or any other language that you want to work with. Okay, let's dive a little bit into this, right? So, NLP pipelines in the past, or not in the past, like previously, they used to have an insane amount of English, like grammar rules and like all these, comma splices and a ton more, right? I can't name all of them. And they used to use those, and they probably still do. They, use those to, run their applications. But we've gone a step forward from, having to write down all of these different obscure rules. English has a ton of exceptions, right? So, yeah, it's hard. You might miss one, and it's just not as precise, right? Because you're doing it yourself, right? And so now we're in this, the day and age where the machine's going to do it itself. Ask the model to learn that information. Ask it to make an analysis, and ask it to predict on new data, right? You don't need to spoon feed the model all these different grammar rules now, okay? And this is what deep learning brought about. Okay, so previously, what used to happen, a ton of grammar rules. Now we have deep learning, and the model will learn these rules by itself, okay? So let's just dive in and look at an example and just get a feel for how this all works. So what we're going to be using in this video is Jane Austen's Pride and Prejudice from Project Gutenberg's website. And, Project Gutenberg has a lot of digital, right? First of all, it is a digital library where we have a lot of free books that we can read. And so we're going to be dealing with Jane Austen's Pride and Prejudice. Okay? So there are two ways in which we can analyze text. Okay, we can either do it, or at least for one hot encoding. Okay, remember one hot encoding. If you don't, you can watch through a few of my videos. For the first one, it's titled One Hot Encoding, and it really introduces it to you. And in a few of my tabular data videos, and also the time series videos, have and incorporate this one hot encoding. Okay, so there are two ways to deal with this data, right? One is at the character level, okay, expected, and you might guess that the second one is at the word level. Okay, so there are two approaches to looking at this text data. Okay. Okay, great. So let's start off by, just loading the data, and then we can look at these two methods. Alright, so we'll first start off with the character level of them. Okay, and let's say with open, okay, Jane Austen .txt, okay, so it's a text file as f, so we're referring to the file as f, Okay, text is equal to f.read. We're just reading the text file. And yeah, so if we print out text, we can see that. I downloaded it in the same exact spot as my Jupyter notebook. And so that's why we don't need the exact path, because it's in the same spot, it's in the same directory. I would recommend downloading this text yourself, or downloading some other text that you want to experiment with and checking out how these two approaches work. Okay, so yeah, let's run it. Okay, once again, it's actually not in the same spot. I'll be right back and I'll just put it in the right spot, and yeah, I'll continue. Okay, I'm back, you guys. Now when I run it, it's great. Okay, so okay, let's start off with some background. Okay, background on characters. Okay, so how do we represent characters? Well, each character, okay, can be represented by a unique code. All right, and a code is just, a sequence of bits, and like depending on the type of encoding that we're doing, whether it's one hot encoding, integer encoding, or whatever, we can have, a different length, right? The bits can be a different length, and we do this so that each character can be uniquely identified. Okay, so each character has a unique identification. Okay, and it's a number. All right, and ASCII 2. Okay, that's the most basic thing you'll see. ASCII 2 was introduced in the 1960s with 128 characters. Okay, so we have 128 characters. And for languages that aren't English, we'll have a ton of other accents and, other characters. But let's just stick with English for now. So this definitely doesn't cover all the symbols, right? Like the accents, the upside down question marks, and, the different characters that are used in other languages, right? 128 is far too small to cover the broad range of things we have in this entire world, right? So, the standard encoding that does do this is Unicode. All right, and in Unicode, there are several popular encodings, which are UTF-8. And encoding is just, you're representing it in a different format that's required for the particular situation. And what do we need in this situation? Well, we need to convert our characters because our model doesn't understand the letter A or this symbol T, right? We need to, it's all numbers. It's just, like I say again and again, like a neural network is just this web of mathematical functions. And so it thinks and learns in math. And so we need to turn this into numbers, right? So yeah, we have UTF-8, we have UTF-16, and UTF-32. Okay, so these are the different number of bits that you can have. Okay, so each of the different numbers, 8 bits, 16 bits, 32 bits. Okay, so let's just leave that as popular encodings. All right. And strings also in Python 3 are Unicode strings. Okay, so you can print out a specific Unicode character or the value that it has in Python if you wanted to, if you're curious. And each character, okay, so first of all, machine learning and everything, we deal with tensors, okay, if you don't know already. Okay, tensors play a big part. Okay, so 1D tensors are vectors. And so we're going to be representing these characters as vectors. Okay, representing characters as vectors. All right, and okay, so this is just one hot encoding. Okay, we have a vector of length x, where x is the number of classes we have. So I'll use this example again. We have 3 different animals that we want to classify. We can't just pass in elephant, giraffe, or rhino. Okay, we need to represent that using vectors. And each vector of the 3 animals that we have are going to be represented using 3. Okay, let me repeat that sentence. We're going to have 3 vectors, okay, and each vector has length 3, okay, because there are 3 animals. And so each animal will have a non-zero value, only one non-zero value, but they're all going to have that same non-zero value at different index points, okay, at different indices. And so that's how we can distinguish between the 3 animals, is because like we have that non-zero value, which is most likely 1, at different points in that vector. Okay, so that's how one hot encoding works. Okay, and that's what we're going to do here. Okay, like I said, the vector is going to be containing all zeros. Okay, but the one non-zero value at a different index each time. Okay, so since we're just using English, right, this will be enough for us. Okay, ASCII 2 will suffice. And you know, let's read it. Okay, so we did that here. Okay, in this simple block of code, this width block. And let's say that lines is equal to text.split. Okay, what are we splitting it based on? We're going to be splitting it based on the line. How do we do that? Well, the escape character for line is \n, or /n. I don't know, \n. Okay, and let's say that a specific line is the 200th line, or actually the 201st line. Right? So let's print out line. Lines. Okay, so we're reading the 201st line, I believe, and it says, "Impossible, Mr. Bennett, impossible. When am I not acquainted with him?" When I am not acquainted with him, okay? And, you know, let's create a tensor that can hold this line, okay? Let's not deal with the entire thing at once, right? Let's just deal with one line, and which is why we're doing this in the first place, right? So let's say that letter T is equal to torch.zeros. Okay, this is a factory method that initializes the tensor with all zeros, and it's going to be of length line. Okay, that's the first dimension, and it's going to be 128 because we have 128 ASCII characters. Okay, so there's 128 different like numbers that we can use to, or actually, yeah, these are characters, and we have an encoding for each character. Okay. So when we have 128 lines, 128 characters here, we're gonna have like each character have a vector that's 128 elements of length, and like a certain index value is going to have that non-zero value that I was talking about. Okay, so that's what's going to happen here. And note that letter T is going to hold a vector per row. Okay, so we have like we have a lot of characters here, right? So we're going to have a vector for each of these characters that's 128 elements long, okay? And you see where I might be going with this. Okay, maybe not just yet, but I'll let you know soon. So yeah, let's run this. Okay, we didn't import torch yet. Okay. Okay, good. So let's say for I, comma letter, in enumerate. Okay, and we'll talk about what enumerate does in a second. Line.lower, okay, dot strip. Dot strip just gets rid of all of the trailing spaces, both at the beginning of the string and at the end. And yeah, so, okay, so letter index is equal to ord. Okay, letter, if the order of the letter is less than 128. Okay, so this is a ternary or ternary operator, which just defines a variable based on a certain condition, as you can see. And letter T, I, and letter index, because this is a multi-dimensional array, it's actually 2 dimensions, right, because we defined it as such here. Let's set it equal to 1. Okay, so what I'm doing here is, well, first of all, enumerate just, returns a tuple of, like, each of your iterations, and it keeps track of how many iterations have gone, and that's what the index is about, right? And so an additional piece of information that might be very helpful is what ord does, and ord actually returns to you that Unicode integer that integer that represents that Unicode character, and yeah, so we're setting equal to 1, whatever, like, we're setting equal to 1 that element. We're setting the element to equal to 1 if, like for every iteration, right? Like for the one hot encoding, we're putting it in at a different index every time. So when you loop through it, right, you get a letter index, okay? We're setting it equal to the Unicode, we're setting it equal to the integer of the Unicode character that we're looking at, because each one of these is a Unicode character, right? When you scroll up here, when you look at this line, each character is a Unicode character, and so for each character, we are setting the letter index equal to the integer that represents that Unicode character. If it's less than 128, obviously, right, because we're just dealing with ASCII too. And if that is the case, then we're setting the value in that 128 element vector. We're setting that specific element of that specific index in that iteration equal to 1. Okay, so this is the filler value. This is the non-zero value that I was talking about. Okay, and yeah, so that's what that's doing here. But you can see this is quite cumbersome, right? And quite not manageable at all. Because if we have like a ton of lines, if we have like, if we're not just looking at the 200 lines, but if we're not just looking at the 200th line, but we're looking at the lines leading up to it, we're going to have an insane number of vectors and insane number of elements, because each one is 128 elements. And so, maybe we should try at stuff at the word level now, right? Because I don't think characters is that feasible. Okay, so let's take a look at doing this one hot encoding at the word level. Okay, so let's try that. Okay, word level. All right. So let's try the word level. We you know, have a better vocabulary here, right? The words actually have meaning now. We're not just looking at the characters in isolation. Okay, so that's a need. We need to establish vocabulary. We can't, you know, we can't just deal with letters all the time. Does the fact that the letter S, I mean, it might, but like, does this letter S tell you more than, you know, this entire word impossible? I don't think so, right? Impossible has so much more meaning, and it contributes so much more to the overall understanding of this sentence, right? So, or at least this line. Yeah, so we need to establish a vocabulary, and since there's so many words in the vocabulary, you know, this character level thing doesn't seem to, you know, cut it, because we have, first of all, we have like a lot of words, and second of all, if we need a vector for each of the characters in that vocabulary, where it's going to be so inefficient. So let's try doing it at the word level and see if it gets any better. And yeah, actually, when I said that, I brought up 2 points. First of all, the characters, like if you have a sentence, you have more characters in that sentence than you do words. But you also have a lot of words, right? You have a big vocabulary, and also doing it at the word level might not also seem like an attractive option. So we'll talk about embeddings in our next video, and we'll talk about it once we're done talking about one hot encoding. And so you'll see how one hot encoding works a lot better with the data that we were working with before, you know, with tables and categorical values, and when you have like, you know, 17 columns or things like that. But if you have like a whole paragraph, or like even, you know, just like a book, or actually I was going in the opposite direction, but you get my point. Yeah, so, okay, but let's talk about the word level. So we can populate a tensor with one hot encoded vector per word. So instead of, you know, like 1, 2, 3, 4, however many characters there are, instead of having those many vectors, we'll only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If I'm not missing any, like, I'm not missing anything. Okay, so yeah, it's better, but we have another problem that we'll need to face later on. Okay, so let's define a function that does that. Let's define clean words. And we'll have an input string. And we'll define all of our punctuation that we might encounter. Punctuation. Okay. And that's gonna be period, semicolon, actually period, comma, semicolon, colon, quotations. Okay, good thing I have single quotes here, otherwise we would run into problems. This quotation, exclamation point, question mark. Let's finish that. It's weird. Okay, so, and underscore. and a hyphen. I'm probably missing something. Don't freak out. Okay, but I think I've covered most of it, if not all of it. So let's have a word list. Let's build our vocabulary and say it's our input string. Dot lower, so we're not confusing ourselves with anything, because it's ASCII. Actually, never mind. Yeah, so we're not confusing ourselves with anything. Dot replace. Okay, so these are just built-in Python functions. Okay, backward slash n. Okay, comma. Space. So we're replacing a line with a space. Okay, and let's do dot split. We've already talked about that one. Okay, word list is equal to, let's do some list comprehension here. So word dot strip. Let's strip it of all of the punctuation. And we're going to do this for every word in word list. Okay, and let's return word list. Okay, so words in the line. Okay, since we're only dealing with this line that we've defined up here. This impossible Mr. Bennett. And let's say it's clean words. And pass in that line. Okay, and let's print out the line and the words in the line. Okay, we're expecting to see, you know, a list, right? Because we're doing some list comprehension here. Okay, so great. We have our line, and we have the words in the line, all lowercase, all stripped of the punctuation, so Mr. doesn't have the dot at the end, the period at the end. Okay, so let's say that word list is equal to sorted. Let's turn this into a set. Okay, clean words. And let's do it for the entire text. Okay, let's pass in the whole text. Okay, and let's say word to index dict. Okay, we'll talk about this in a second. Okay, so word I for I comma word in enumerate word list. So this is dictionary comprehension. You might be less familiar with that, but it's pretty much the same idea, except we have both key and value. Here, enumerate, we talked about, it runs over an iterable and keeps track of how many iterations there were. Okay, so there's a mapping of keys and values going on here. Okay, so yeah. So let's take a look at the length of word to index, dict. And let's take a look at word to index, dict, impossible. Okay. All right. So we have the length, which is this, and we have something for word to index, dict. So what is this here? Well, as you can see, right, this is a dictionary, and we're just printing out the number of keys, which is the same number of values, and this is the key, the value of the key that we're printing out. All right. So let's hot encode it. So let's say word t is equal to torch.zeros. Actually, did we do this already? It's basically the same thing as what we did with the characters, except for now, we're doing it with words. Okay, there's no difference. Except the differences that we've already highlighted. Okay, words in line. Okay, len of word 2. Okay, let's see if this, okay, good. So for I in word in enumerate, okay, words in line, you'll see the insane similarity here, right? For I letter, no. For I word, you get what I'm saying? So word index, just like we did letter index, is equal to word to index dict of the word, so the value of the word at of the key word, and word t I word index is equal to 1. And don't worry about the formatting, okay? We'll just see it when we print it out. Okay, so we have some stuff going on here. Okay, dot format. Okay, we could do F strings if we wanted to. Word index, word. Okay. So when we print, okay, first of all, it's already printing, but at the end, let's print out the shape. Okay, what's wrong? I put a colon here for no reason. Shouldn't be indented. Zeros. Okay. So we see some 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is the last word him? Yeah. Okay, so we have the indices. Okay. That's what enumerate does. It counts, or rather it keeps track of the number of iterations that have gone on. Okay, so that's pretty handy. Okay, so what did we print? We printed out I. We printed out the word index. And we printed out the word. So, yeah. That's the shape. We have 11 words. And this is the number of words in our dictionary. It's a lot, and we only looked at like one sentence. Imagine if we had a whole book. Okay, it's gonna be hard. Which is why, this isn't that suitable. I just wanted to show it to you because, well, first of all, if we set bounds to the vocabulary, and if we're only dealing with a small subset of it, and if we're only dealing with some small amount of text, I guess we could use this, but, yeah, so this is another way you could potentially use one-hot encoding, although there is another, more effective way of doing this, using embeddings, which we'll talk about in our next video. So where's the trade-off here? What's going on? What's this competing, problem that's happening here? What's the problem if we use characters, and what's the problem if we use words? Well, characters are just a few classes. So I'm just wrapping this conversation up, but, characters are just a few classes, and, the vector size is going to be small since those are the number of classes. And we can work with those. Those are small enough sizes of vectors that we can work with. And this works out because in most languages we have a fewer number of characters, so there's a smaller number of classes than words. But words, on the other hand, it's a completely different story, right? We have a huge vocabulary. We're gonna have tons and tons of words, right? It's gonna be insane. And let's just pick English for simplicity, right? We have a certain vocabulary and we have a lot of words, right? There's a lot more classes, and you know, it's a lot less manageable. But the one reason why you might choose words is because it has more meaning. You know, like we've talked about, it adds more depth to the sentence. It adds more meaning. But we have a problem with that. We still have a problem if we choose words, right? It doesn't solve all the problems. So, which is why we'll be talking about embeddings in our next video. Okay, I hope you learned something new today, and yeah, don't forget to like, comment, and subscribe.